Good evening, everybody. My name is Jason. I'm a second-year engineering science student at the University of Toronto, and today I'll be talking about the course ESC 103, Engineering, Mathematics, and Computation. Today is December 19th, 2021, and I'm making this video because I no longer have to write my final three final exams because they were canceled by the university, so I have time to make some videos about some previous courses I've taken in my undergraduate degree. So what exactly is ESC 103? As I mentioned, it's a course that I took last year. It's a mandatory year one fall course in the Engsci program at U of T. When I took the course, uh, Professor Cluett was the instructor. So the main course topics included an introduction to vectors. We went over definitions of dot product, projections, cross product, etc. And we looked at vectors in a geometric lens by looking at how we could define lines and planes using vectors. We went into solving linear equations and representing systems as matrices and looking at matrices as transformations. Working more with matrices, we also covered eigenvalues, inverses, and determinants, as well as the reduced normal form of a matrix. So we talked about Gaussian elimination. We also talked about rank and how that relates to the AX equals B problem. For example, when it comes to the existence and uniqueness of solutions of the system. We also talk about numerical methods like numerical integration, boundary value problems, etc. And a lot of that we did using MATLAB, which was a key component of this course. Every week we had a MATLAB tutorial session where we talked about using MATLAB for different engineering math and computation problems. Um, and to be honest, I think it's a pretty useful skill. It's definitely been useful for other courses that I've had to take, for example, Mat 292, which I took just this fall term. And I think MATLAB is a very powerful tool and very useful. So today I'll be covering an exam question from the final exam I took almost a year ago, December 21st, 2020. I'm going to be talking about question 2. This final exam had 6 questions. It was administered online because of COVID. Um, so this question talks about linear regression, linear combination of vectors, the least squares problem, um, as well as the normal equations, which requires an understanding of the matrix transpose. So let's just dive right into it. This question has 3 parts to it. Parts A and B are related. Part C is separate, but the concepts in this question still relate to A and B. So in part A, we're given 5 data points, and we want to know what condition must be satisfied if we want these 5 data points to lie on a straight line that can be modeled by y equal to cx plus d, where c and d are unknown parameters. Part B asks us to find the least squares line of best fit, y equals cx plus d, that will fit these 5 data points. And part C gives us another 4 data points, but wants us to find the least squares constant that will best fit these 4 data points. So it would be in the form y is equal to d, where we only have one fitting parameter. And it wants us to do this using the associated normal equations. So let's start with part A. We're given 5 data points that I've listed on the screen. We know that we want all these points to lie on a straight line, y is equal to cx plus d. And in order for this to happen, we know that each point xi, yi must satisfy yi is equal to cxi plus d. So we can write that out like this, where I've just substituted all our y values on the left and all of our x values on the right. But this is kind of clunky, so we can do this in matrix form. So we can write ax is equal to b. B is a vector containing all of our y values. X is a vector containing our 2 fitting parameters, or I shouldn't say fitting parameters, they're just our parameters, c and d, where C is the slope and D is the y-intercept of our line. A contains our x values as well as a column of ones, which will all be multiplied by the constant D to represent our vertical shift. We can also represent this as a linear combination of vectors. If you recall 2 slides ago, we had 5 equations. These are the same 5 equations, but we've just written them as vectors and taken out the scalar multiples C and D. And what you'll notice about this problem is that on the right-hand side, we still have our vector B. And how we formulated this problem is we want the condition that must be satisfied for all 5 of these points to lie on a straight line is that B must be able to be represented as a linear combination of the columns of A. So notice how this is just the first column of A, and this is the second column of A. And there must be a linear combination that satisfies this. But it should be pretty clear to see, just looking at the last 2 lines, or 2 rows, I should say, of these equations. It's not possible that we satisfy these two with non-zero values of C and D. And if C and D are 0, then these other 3 equations aren't satisfied. So you see it's not possible for all these points to lie on a straight line, but the question is not asking for that. The question is asking for what condition should be satisfied if they do. And this is the condition that must be satisfied. So just to recap, the 5 data points lie on a straight line only if the B vector or Y values can be written as a linear combination of our X values as well as this column vector of all ones. So part B, let's find the least squares line of best fit to these 5 data points. And we'll do this using the normal equations. So I'm not going to go over the derivation of the normal equations, but essentially how you would go about it is you would notice that in general, if we want to find a best fit for our data points, we can frame it as an AX is equal to B problem. So we want a vector X of fitting parameters such that AXLS will be as close to B as possible. And the way we formulate this problem is we'll project B onto the column space of A. And we'll say that the projection of B onto the column space of A is equal to our sort of best guess approximation. And what we can do then is we can define an error vector to be equal to B minus AXLS. And you'll notice that because AXLS is a projection onto the column space, B minus AXLS is orthogonal to each of the column vectors in A. And because of that, we can say the dot product of each column with the error vector is equal to 0. And what we'll see, we should have n equations that are equal to 0, which should mean that A transpose multiplied by B minus AXLS should be equal to 0. And if we distribute that out, we get these normal equations. So I know that must have been sort of tough to follow, but just take my word for it. And recall that from part A, we have our definitions of A and the vector B. So we can calculate A transpose A and A transpose B. A transpose A, we can easily take the inverse of because it's a diagonal matrix. We just take the inverse of the diagonal elements, and we can calculate our least squares estimate for our fitting parameters, which are C and D. We find that C is equal to -1 and D is equal to 1. So therefore, the line of best fit is given by Y is equal to minus X plus 1. So part C, let's do the same thing, but we're given 4 other points. So this is totally separate. And, excuse me, rather than fitting any line, we're just fitting a constant. So Y is equal to D. And what is our least squares estimate? We can formulate the problem again using an ax is equal to b approach. In this case, a is just a column vector of 1s because d is just a constant, and b is once again our y values. Notice how the x values actually don't matter here because we're fitting just a constant. So we can once again use our normal equations, replacing xls with dls. And because we know A and the vector B already, we can calculate A transpose A, which is just a constant 4, and A transpose B, which is just a constant 36. Taking the inverse of a constant is just 1 over that constant. And so we find that our least squares value of D is equal to 9, which means that the constant of best fit is given by y is equal to 9. And notice we could have just taken all the y values in B, summed them up, and divided them by 4 because there are 4 data points. So we would be taking the mean value, and that would have given us the constant of best fit as well. But this is sort of a more rigorous way of showing that this is the least squares estimate. So before we end off, I'd just like to make some acknowledgements. Thank you to Professor Will Cluett for the amazing course content, as well as for this final exam question. I do not take any credit for writing this question at all. I also like to thank my MATLAB TA for the weekly MATLAB tutorials. I found them to be very helpful, so thank you, Nima. And I'd also like to thank the individuals who I stole parts of my presentation template from. And yeah, thanks so much for watching. Take care.